All right, so as promised, I want to give you a video on two sections in chapter 6, beginning with section 6.1 on page 409. And in this chapter, and we're only going to look at two sections here, they will be on your next test. This chapter deals with solving what's known as a differential equation. A differential equation is simply an equation that has derivatives, maybe other things of a function going on in it. So typically, when I solve just a regular equation, I'm getting a solution of x equal to 5 or something, or whatever. But with a differential equation, we're getting functions that satisfy the original equation. And so in section 6.1, that's what we're looking at. Or can I come up with, can I verify that a function satisfies a given differential equation? And so that's what we're doing on page 409. Let's begin with number 2 on that page. Number 2, I have a function, y equal to e to the negative x. And so the question is, does that satisfy this differential equation? Y prime plus 4y equal to e to the negative x. And so again, if I want to verify if it's a solution, we're going to plug it in to be able to do that. And so I have a y that I can plug in here. What I don't have is y prime. So let me pull over and find that. The derivative of y, and I'm differentiating e to the negative x, so I always get back what I started with, plus the derivative of negative x, in this case is negative 1. So I'm going to take all of that and plug in for y prime. I'm going to take the original and plug in terms of y, and I want to know, is it true or not? So we have 3 times the derivative plus 4 times the original function. I want to know if that makes it be a true statement or not. And I think we probably can see that it's going to. If I do some multiplication, negative 3 and 4, e to the negative x, those are like terms. So when I combine those, I do indeed get e to the negative x, which makes both sides of that the same. Therefore, indeed, it's a solution to that problem. Look at number, maybe some that are more interesting. Let's look at 20. And look in your book and read those directions carefully on number 20. It says to determine whether the function is a solution to this differential equation, so again, this is the problem that I want to solve, and I've got a whole slew of possible solutions to that to use. So number 20, my problem is y equal to x squared e to the x. And so again, I'm going to plug that in this spot for y, but I'm also going to need its derivative, which is a product rule. So first, derivative of the second, plus the second derivative of the first. And y'all know I like to clean it all up, so let me quickly do that. All right, so I'm going to take all of this and plug in place of y prime. I'm going to take all of this and substitute in place of y, and then examine if it's a true statement or not. So I have x times y prime minus 2 times y. And I want to know, does that give me x cubed e to the x for a solution? So let's multiply that out. So I get x cubed e to the x, so I'm feeling good about that, plus a 2x squared e to the x. And then in the second set of multiplication, a negative 2x squared. So again, I think that's going to be a solution. Those things add away. And again, that checks out. If it doesn't check out, it doesn't check out. It'd be not a solution there. So maybe number 22, I'm looking at the function sine x. and I'm still trying to solve the same differential equation, or verify if it's a solution or not to that same equation. So again, I'm going to need its derivative. The derivative of sine is cosine. So let me plug in both y and y prime into that same function. So x times y prime minus 2 times y, and I want to know, does that equal this thing? And clearly looking at that, it's not going to be a solution. Okay, so those problems aren't bad at all. I want to look at one more from this page, number 32, just because it allows us to do something a little bit different with number 32. Number 32, it says to verify that the general solution satisfies the differential equation, and then find a particular solution. So I have a general solution. That's actually kind of what I've been working with. 3x squared plus 2y squared equal to some constant. I don't know what the constant is, but I can still see if that satisfies the problem or not. And then the differential equation that I'm examining is 3x plus 2y, y prime, all equal to 0. So the first thing I'm going to do is to take a derivative over here, and I'm going to have to use implicit differentiation to do that. And then I'll plug in everything into this dE to see does it satisfy it or not. Okay, so derivative of the general solution. I'm differentiating with respect to x. So that becomes a 6x. And then I'm differentiating y's. Remember, every time we take a derivative of y, we've got to include a y prime. So 4y, y prime, and the derivative of a constant is 0. So let me see if I can solve this in terms of y prime. So I'll move 6x to the other side and divide both sides by 4y. It looks like y prime is a negative 3x over 2y. So again, I'm going to take that and plug in up here, and we'll see does it satisfy that or not. Typically, we're also plugging in terms of y. This is a little bit tricky to solve in terms of y, but I think it's going to verify that it's a solution without having to do that. Let's see. So 3x plus 2y times y prime. I want to know, does that equal to 0? And the two y's add away, or divide away rather, and so I'm left with 3x minus 3x, which is certainly 0. So indeed, this is indeed a solution to the problem. So then let me use the next part. The next part of that says, okay, whenever y is 3, x is equal to 1. So we call that an initial value. An initial value problem. And y'all, it can come in lots of forms. If I'm writing, just thinking of cloud for a moment, if I have a function like this, equal to some function of x, whatever, it's not really a true statement, so it's a function of x. Then one way to say this is whenever x is 1, y is 3. So there's several correct ways to do that. So, but I can plug both of these conditions into this part and find c. So x is 1, y is 3. And I'm going to square all of that. Hopefully my arithmetic is going to be okay. It looks like c is 21. So what that tells me is I have a particular solution that looks like 3x squared plus 2y squared all equal to 21. Not only does that satisfy the original differential equation way back up here, but when I let these x and y values get plugged in, it gives me a 21. So a particular solution is what we call that, as opposed to, a general solution. Okay, So in section 6.1, that's all you're doing is verifying solutions and being sure that they work. In 6.2, we're actually going to find some solutions of those things.